Good morning. Today I'll talk about this topic, ultralight axion dark matter, its impact on the halo structure. This is work done with a student from Hong Kong, Cheung, and his advisor, Chu, and research fellow of NCTS, Chai. And I also put a reference to this topic, which appeared a few days before our work. I found that I learned quite a lot from this paper by some famous people here. And our work mainly focused on the n-body simulations. Okay, so how light is this guy? Actually, this guy is very light. And the purpose why it is so light is to make sure that the debauchery wavelength is long enough, okay, such that it will contribute to our understanding of the galactic structures. Okay, so let's just flash you a few evidence that why we believe in dark matter. The first one, we all know that the rotational velocity of the galaxy turn out to be much larger, kind of flat, unlike the predictions. So that means that there are something inside that we have not seen. And more stronger evidence coming from gravitational lensing, we all heard about that. That is a bunch of mass that we do not see, but bend the light. So, and also this one is more recent is the bullet cluster. Essentially, the collision of two galaxies, and the central part there are some hydrogen gas and baryon. Because of friction between them, they stay there and radiate some X-ray. On the other hand, the dark matter have very few or almost no interaction, they just go through. And this coloring are just artificial. Okay, so, and the dark matter is very important to our the structure formations. And also, is we can see that the dark matter density actually can estimate from the CMB power spectrum. Actually, I start to learn a little bit how to read this, and please bear with me. There's some terminology that actually I just recently learned. So it was the third peak that tells us how much dark matter density that should be there. All right. And turn out that this is our universe budget, that the dark matter is approximately 3% of the total energy of the system. And this one, we found, in the n-body simulation, we found that actually the dark matter is very important to form the potential before the baryon that can fall into the potential before the structure formation to start. Okay, so far we know that there should be dark matter, but unfortunately, or fortunately for theorists, the identity of dark matter is really unknown. Okay, so these can still keep writing papers or building experiments to tell what exactly it is. Okay. So this is the graph that I just talk about the gravitational lensing. And now this is our Milky Way galaxy, and this is our disk, and this position of our sun. And turn out that in this halo, there are a lot of subhalos. I'll come back to this picture in one slide. So we only know that dark matter should exist throughout the universe. The identity, we don't know. So the standard model of cosmology is called lambda cold dark matter model. The dark matter has to be cold, long relativistics. All right? So the dark matter, actually, right now we know that consists of some unknown elementary particle produced in very early universe, and we found that it is cold, such that the velocity dispersion effect on the structure formation is very negative. All right? And this model can explain mostly all the features in large scale. However, for a smaller scale, like less than 10 kiloparsec, that will be inconsistent with observations. And there are fields, maybe most of you will have heard that, the small scale crisis, too big to fail problem, missing satellite problem, and the cut-score problems. Just give one slide each to explain what are they. Okay, before I come to that, this is just a summary a very brief summary of dark matter candidate. The most popular one is the WIM, with interacting massive particle, and actually there are many theoretical models that predict the existence of such particles, like RSP, like the supersymmetric particle in SUSY, like the p-periodic particle nucleus model, LKP particle in the UED model, and some hidden sector fermion, etc. You can name it. And the other type is ultra weak, like axion, axino, gravitino, right-hand neutrino, and so on. There's another type which dark matter actually is decaying as long as its decay time, lifetime is about the same order of the age of the universe. That should be okay. So a large experiment actually has been designed to detect the WIMPs because they have some interaction that maybe be able to see that. For the other type, this one, very difficult, but not hopeless. So this is a famous diagram to say we can detect the dark matter in all directions. All right, like the direct detections, like the standard model. This is dark matter particle come in and scatter with a standard model particle within a nucleus, either the nucleon or the electrons. So we detect the recoil of this nuclei to detect the dark matter. At the collider, we can study the standard model particle annihilate into dark matter particle. The experiment will measure the missing energy and compare with the standard model predictions. Another type is the indirect detection. The dark matter annihilate into standard model particle, and the standard model particle will eventually go into the positron, gamma ray, neutrino, and we have been building detectors to see all these kind of exotic particles. All right, that's another type of test for the dark matter. Namely, for example, the self-interaction of dark matter. All right, that will certainly affect the galactic formation, rotational velocity, CMB, etc. And so we can right now we can get constraints and also some useful information from all these measurements on the dark matter interactions. So this is this kind of small. I don't mean you to read very carefully. Just to tell you, in the proposal of dark matter particle, it can be very light, ultra EV, and all the way up to gut scale. They are all possible candidates. The reason and of course, because we don't know anything about dark matter, the identity of that, we can still keep writing paper on a whole spectrum. All right. Now, cold dark matter seems to be very successful, but however, it also